Okay, thank you everybody for joining. Today, the webinar will be about my experience as Cat3 checker in the modeling of the River Irwell network arch bridge. Okay, so today's presentation is going to go through the points that are listed here. We're going to go through an introduction to the bridge. We're then going to go through an introduction of what a network arch is and how it compares to a typical bowstring vertical hanger tied arch. We're going to go through an overview of the model, how the model is created, and the features that I like the most in MIDAS Civil while dealing with this type of bridges. I'm then going to take you through the construction sequence analysis setup for this specific bridge. I'm going to give you a brief introduction to moving load analysis and how this is carried out for cable supported structures. And then I'm going to show you the results obtained from the model against the results from the structural health monitoring on site. The takeaway from today's presentation, I hope, will be what a network arch is, how you model cables in MIDAS with different features, some of the features for MIDAS in geometry construction, how to build an influence matrix directly from the functions available in MIDAS, how to set up a construction stage analysis, how to model concrete slab decks when they act in tension members, and how to use moving load analysis when you're dealing with cable supported structures. Before we start, I'm going to introduce myself. I'm a principal engineer in AECOM. I moved to the UK 6.5 years ago, finished my master's in bridge engineering at the University of Surrey, after finishing my first master's at the University of Genoa in Italy in construction engineering. I'm a chartered member of the ICE in the UK and the CNI in Italy, and I am a member of the editorial panel for proceedings of the Institution of Civil Engineers, Bridge Engineering. Over the last years, I've gained experience on the design and modeling of cable supported structures, having had the possibility of working on multiple cable stayed bridges, arch bridges, both as designer and checker as this one, and on the assessment of some suspension bridges and works on site for a UK suspension bridge. As I mentioned, I work for AECOM. I think most of you will know the company. We are a big consultancy counting 56,000 employees worldwide. And this year we've been named #1 transportation, environmental, and building design firm in the ENR ranking. Okay, moving on to the bridge. The bridge is located in Manchester and is the centerpiece of a wider project called Ordsall Court. The bridge connects the station of Victoria and Piccadilly in Manchester, and it presents this peculiar squash tennis racket shape, which made it really famous. At the time of construction, it was the longest spanning asymmetric network arch rail bridge in the world, and it was the first network arch bridge to ever be built in the United Kingdom. The total span of the structure is 89 meters, and the arch rise is 13.57, so the structure is very slender. To obtain the continuity from the arch to the approach spans, an architectural feature was used, which is made of non-structural reverse curvature arch component, and this became a bit the signature of the bridge. In terms of plan view, you can see the deck is 15.4 meter wide and carries 2 railway tracks on a curved alignment. It's designed for full LM71 loading, SW0 and SW2 as per Eurocode's definition. The construction of the bridge made use of asymmetric towers, which we will see are placed here and here. And this was done to gain on the construction program by reutilizing the towers that were used to dismantle the previous truss bridge at the same location. Before we dive into the presentation, I want to mention some of the people that worked on this bridge. The bridge won several structural and architectural awards from various institutions such as ISTRAC-T and RIBA, and it really has been the effort of many different people working in a constructive manner together. So the owner, Network Rail, the architectural firms BDP and Knight Architects, the structural engineering carried out by a joint venture between AECOM and Mott MacDonald, where Mott MacDonald acted as designer and AECOM as independent checker. Contractors BAM Skanska, again acting in a JV, the steel fabricator Severfield, and the structural health monitoring on site provided by Datum and Pfeiffer. Okay, so moving on to the elements that make up the bridge. The arch cross-section is made up of bespoke fabricated sections with a varying depth and width from 700 millimeter to the south end to 2,500 millimeter in depth at the northern end. The plates also change from south to north from 40 to 60 millimeters in thickness, and in order to enhance the overall appearance of the bridge, the arch are inclined in the plane by 6 degrees. The tie beams are also fabricated welded elements with the webs and the top flange inclined to meet the hangers in their plane. The connection between the hangers and the top of the flange is obtained through clevis plates, as you can see in this picture here. The hangers are made of proprietary bars, and they're arranged in 2 different planes, 210 millimeters apart, and they're not connected between the planes. The hangers will be stressed in 2 different phases, as we'll see later. And the tensioning is done through the use of a turnbuckle system provided by the manufacturer. And a total of 46 hangers per side is present per arch on the bridge. In terms of the deck is a composite deck made using a C40-50 concrete slab over permanent participating formwork. And for this type of bridges, if you go through the Eurocode, there is a high concentration of forces, transfer of forces at the nodal ends. And there is a requirement for a number of studs and very stiff transfer of forces here. And I'm leaving here the clauses of the Eurocode for you to check. Here it will also define what a tension member is. As I was saying, the concentrated forces come into the node, and it's a typical detail of network arch bridges to use this type of joint. It's usually called a knuckle joint. And this joint is basically connecting the tie beam to the arch by using a stiff plate that enters inside the arch. And effectively, we will see later what this really does, but basically it eases the transfer of forces from the arch into the tie beams by spreading it over a longer area. In terms of articulations, the bridge articulation is shown here. We have a fixed bearing at the northwestern side, and as you can see, there is no expansion bearing along the span of the bridge. Before we move on to the model itself in MIDAS, I wanted to touch on what is the definition of a network arch and how it is different from a bowstring arch. So the typical bowstring arch scheme is shown here in a picture. It can have vertical hangers, like in this case. The hangers can also be inclined when we have a Nielsen type bowstring arch. And under UDL, what happens is that the arch is in pure compression. The springing force is taken by the tie beam, which acts in tension. So we're not sending the thrust to the soil, to the foundations, but we're actually taking it into the tie. The network arch bridge can be considered as an evolution of this concept. The concept itself was introduced by Professor Tveit in the 1950s during his MSc dissertations in '55. The definition that he gives is that the network arch is a tight arch where the hangers are inclined and cross each other at least 2 times. And Professor Tveit spent a lot of time in his career researching this type of bridge. The picture that you see here is the bridge at Steinkjer in Norway. I hope I didn't butcher the name too much. And this was the first network arch bridge to be built in 1963. And many other network arch bridges have been built ever since around the world. So as I said, Professor Tveit has carried out a lot of research, and one interesting part of his lecture is this comparison between the real bowstring arch with vertical hangers at Straubing in Germany that was built in 1977, and his proposal of a network arch made in 1980 for the same span of 200 meters. Professor Tveit calculated the influence lines for these bridges, and he showed that the bending moment induced into the arch and the tie beams is lower for the network arch. This was done considering the same quantities of material in terms of hangers, tie beams, and arches. What this points to is that a network arch can be a very effective structure, which can lead to savings in material, savings in weight, and therefore longer span. So what I tried to do is I've replicated the study that he made in a very simplified way in MIDAS. I've extracted the arch here from the river Irwell. I've recreated a bowstring arch with vertical hangers using the same number of hangers, and I've applied an asymmetric load that you can see here of 600 kilonewton. And I've compared the contours of displacement for these 2 arches. And you can see graphically and in the legend that the difference in displacement is marked, and the bowstring arch shows both higher downwards displacement and higher upwards displacement in the arch. The same can be said for the bending moments. The bending moments diagrams are plotted here for arch and tie beams. You can see that the bending moment for the same load is the bending moment induced in the arch, and the tie beam for the same load is higher in the bowstring arch than in the network arch. I then created linear buckling analysis models in MIDAS just to compare the two arches. Here it's just the arch alone. There is no actual bridge, so transversally the arch is not restrained. I've used permanent loads and the same asymmetric live load that I showed you. And effectively, we can see that the buckling factor, so the load multiplier associated to the first mode for the network arch is 10.29 in value, while for the normal arch, the bowstring arch would be 2.2. The ratio is roughly 4.5, which is in line with what is found in literature for these structures. So recapping what the network arch is, it is a tight arch with inclined hangers that cross each other at least 2 times. In literature, you will find that this leads to lower bending effects in the member, higher stiffness in terms of deflections and buckling against lateral buckling, higher redundancy in the cable out case, and this is due to the fact that basically having so many hangers crossing each other better redistributes the loads from many parts of the bridge, as we've seen through the bending moment and deflection outputs. This will allow us to design more slender structure and bring about savings in material, so will make the structure economical. Effectively, the takeaway from this is that with network arch bridges, we can build longer spans that show higher redundancy, better material utilizations, are more economical, and environmentally less impactful as a consequence. I'm leaving here some reading that I found very useful while studying network arch bridges. This part is general knowledge on the network arch, and these 2 papers from Ruzi Rusev, the designer of the structure, the River Irwell Bridge, will give you more insight into the first one, into the structure itself, the second one, and the overall Ortsal core project. So I recommend you check these papers out. Okay, moving on to the MIDAS model. Here is an overview of the model. As you can see, the arch, the tie beams, the cross girders, you can't see them, and the bracings are all modeled with 3D elements, 3D beams. The concrete slab was modeled using an orthotropic plate, using a material with time-dependent properties associated to it. The hangers were modeled as truss elements, and the fin plate of the knuckle joints were modeled as isotropic plate element. It is important to put them in the global model, because if we think of the way the forces will be distributed between the arch and the tie beam in a FE model, they share one node here, right? So what will happen is that we're going to have a concentration of bending and stressing in this node, which is not realistic. In reality, we have this knuckle joint that spreads the load transfer to a wider area, and effectively it acts as a stiffener in the local area. So having it in the global model is really important. In terms of modeling process, the modeling process of a structure like this is very similar to any other structure. So you start with the definition of material and section properties. I think most of you are familiar with MIDAS. This is done to the property menus for materials and sections. For the sections that I've shown for this bridge, we have fabricated sections. So in this case, the tool to be used is the section property calculator. Once this is done, the result is that we have defined all of our properties in the tabs, and we can move on to defining the geometry of the bridge. In MIDAS, the geometry of the bridge can be input directly from the software using the create, node, and elements tools, or imported from a series of commercial packages. I usually use the DXF files from AutoCAD or any other drawing software. It's time then to define the boundary conditions, the loading conditions on the bridge, and it's very important to do the grouping at this stage. The group is a fundamental part of the construction sequence analysis, and basically MIDAS is based on the use of structural groups, boundary groups, and load groups. Once this is done, it's time to do the construction stage analysis. This can be defined to the construction stage menu graphically, or can be defined through code. Effectively, the idea behind the construction stage analysis is that you specify duration and you specify which groups are activated or deactivated in terms of elements, boundary, and loads. Once this is all done, the model is created in its geometry, loading, boundary conditions, and all the properties, and we will end up with our construction sequence. What I'm showing here is the construction sequence for the River Irwell bridge. We had a total of 103 construction stages, and this is the view that you will see in the 3 menu in MIDAS. And if you expand on any of it, you can see what's being activated, the activated duration, and the additional steps, and so on. Okay, moving on to the features that I used for this model and that I like the most in MIDAS. So as I said, the arch is a tapering section, both in width and in depth. And this can be defined in most packages very easily. You go into your section properties, you define the start, the end, and you define a tapered section. In MIDAS, it would be done as a general section because I'm using the SPC, the section property calculator tool. If we have the arch and we apply this section and our arch is subdivided in multiple sub-elements, the result will be this, which is not quite what you want to get. So how do we go from this to actually the arch shape that we want? So in most packages, what you would have to do is either define all of the different sections in a drawing and then import them, or write some sort of script with looping using array copying in CAD, for example. And you would have to go back to your script and change the number of loops that you're running if you need, for example, to add an additional node because the contractor wants to see if they can use different method of erection for the arch, for example. So I'm going to go to MIDAS and I'm going to show you how you actually do this very quickly through a function that's called taper group. So as you can see here, we have the arch and the sections are not defined as we want them to be. If I use this function, under property called taper group, what I can do is I can create the arch very quickly. All I need to do is give it a name and select the elements that I want to use in my taper group. I have assigned to this arch now a section, which is the one that I've shown to you. So the arch tapered, which has the start at the south and the right ending at the north. And all I need to do is basically specify the type of section shape variation that I want to use, whether I want to use a linear variation or a polynomial variation. If I use polynomial, I can specify the grade of the polynomial equation. And this can be done both in the vertical and the horizontal axis. And I've selected my elements. You can see them in red on the screen. I've given a group. I click add, and MIDAS will create the section directly for me. And this saves you a lot of time. MIDAS has also the function of exporting this section. If you click on convert to taper section effectively, what the software will do automatically is it will create here in your section tab all of the sections that it created for all of the different nodes splitting up the arch, basically. So if I start, this will take a bit, but effectively the model has created 216 sections, I think overall. Yes, you can see them here. And if I click on it, you can see that this will be the taper section going from this node to this node. And if we open it, the section is ready to be imported in any other model, or it's ready to be used, for example, in MIDAS FEA and X to convert to a shell element. Okay, moving on to the concrete slab. As I said, the concrete slab is a tension member as defined in Eurocode, and effectively it acts as an orthotropic plate, given that the tension on the longitudinal side will make concrete crack. Now, the equation for the typical equation that you would find in a structural mechanics book for an orthotropic plate is this one, where the parameters are this. These parameters are not of much use to civil engineers because we don't have the luxury of testing our big slabs on our bridges. But if you go in a book of numerical modeling for plates, you can find these equations which relate the inertias in the two directions of your slab for steel part and concrete part, and the elastic modulus for steel and concrete as found in the codes. So effectively, if we calculate this, we find that these y and g and h, and we can put this here, invert this function here, and what you will get is your result for the Young modulus in the two different directions, which can be directly input in MIDAS into the material data for orthotropic materials. And this is what I did here. This is one way of modeling the slab. The other way can be through using stiffness modifiers. What you do in this case is you calculate your stiffness in the two different directions for actual, so in plane and out of plane responses, and you apply this to an isotropic plate. So you need to specify the material as isotropic. And if you use this technique, you must make sure that you define this plate modifier as associated to a boundary group so that you can activate it correctly in your construction analysis. Another way of modeling this deck could be through the use of beam element. In this case, you would create a grillage of beams. The longitudinal beams are given the cracked concrete beam properties, while the transverse beams are made composite for this type of bridge with the steel transverse girders. And to do that, you use the composite section for construction stage. And what you do is basically you define your beam, you select the element, the section that you want to make composite, you select the stage at which the first part, so the steel part, is activated, and then the stage at which the second part, so the concrete part in this case, is activated. And this can be a third way of modeling this type of deck. Moving on to the cables. Cables, by definition, are non-linear elements. So they are tension-only elements. They do not take any bending, and they show a high non-linear behavior. So based on the level of stress in the element, its stiffness will change. If you want to use a full cable element, you need to use a fully non-linear analysis, making use of the tangent stiffness of the element. However, from experience, you don't need to do this for all structures. And effectively, usually you need the full nonlinear analysis when the span is very long, 500, 600 millimeter plus of span, or when the tension in the cables are low, and so the sagging effects of the cable become dominant. For all other cases, you can actually use an element type in MIDAS that makes your life easier, and this is the truss element. The truss element is, again, an element that only takes actual forces, so you won't be able to take any bending in this element. And MIDAS uses what's commonly called the Ernst modulus for this to define the stiffness of this element. Effectively, the stiffness is made up of an elastic part, like any beam, plus this Ernst modulus, where the stiffness depends on the level of tension, you can see it here, T, and the length of the cable. Now, if we look at what I said earlier, when you have very long span, the length is going to go up, right? If the length goes up, this becomes small. So what you have is a very high denominator and a low stiffness overall of the element. The same concept applies to tension. If the tension becomes low, this becomes very low, sorry, and as a consequence, this will be very low. So you can kind of understand where this comes from by looking at this simplified way of representing the stiffness due to sag effects. If you decide to use cable elements, as I said, the analysis become nonlinear, so you lose the possibility of using superimposition, and you have to specify in the construction stage analysis control data, you need to specify that the analysis is nonlinear here. You see analysis type nonlinear with a cumulative stage control, and in the nonlinear analysis control, you need to specify geometry nonlinearity to take this into account. So you're taking into account the large displacement. You can then use the iteration method that you want here. Moving on to another feature that is available in the construction stage analysis control data that I really like about MIDAS is the possibility of restressing cables using a force control method. Most software will require you to either impose an elongation on a cable that already exists in your model to specify a restressing, or deactivate the existing cable element and activate a new cable element on top of it. If we think of what we give in the drawings to the contractor, for the stressing sequence, we provide them with target forces that they will put inside the cable through jacking, right? So MIDAS allows you to do this directly into the software by using the external force control, and you can decide whether to add the additional force that you're specifying to whatever is in the cable or replace it directly, so get to the target force. What I mean by this is that, for example, if we look at the River Irwell arch, we had two different phases of stressing. The first phase of stressing brings this element 3036 to a force of 505, and this is what you would find in the output from the construction stage analysis. You can see that the force is what's specified here. By using the external control in the construction stage data analysis, I can basically control the target force at the end of the phase where this element is being restressed, and the result will be exactly what I put in the table. So I'm restressing this cable at 285, and this is the result that I read into that cable. In other packages, I would have had to either convert this into an elongation and make sure that the force is coming out, or deactivate this element, the original element, and activate a new element in the same stage on top of it. So I like this feature of MIDAS, and it makes my life much easier. Moving on to other tools that I like in MIDAS, the cable force tuning is a very good tool to interactively change forces in the cable and see the results on your screen in real time. This can help you reduce the number of iterations to find the optimum tensioning. And I put together a video, which I hope will start, where I show how you use it. The concept is based on the use of load combinations. So you create a load combination with permanent loads and the hanger loads, and you access this tool from result cable control, cable force tuning. So what you see here is the load combination. Effectively, we can see the load multiplier for all of the load cases in the load combination, and I define here target output that I want. In this case, I've defined the bending moment in the tie beam and the vertical displacements in the tie beam. What the function allows me to do is basically graphically drag and drop these bar charts that you see there, or enter the number in the table and see live the movement of bending moment and displacement in the deck. You can see them here. Please mind that the numbers that you're seeing here are load multiplier to the load case. These are not the force that is currently into the hanger, okay? So you can see that this was changing live, and I can also specify ranges between which I want my output to be shown. So effectively, this dashed line here can represent, for example, the capacity of my beam, and I can see, and the same can be done for target displacement, for example. And by moving the bar charts, basically, I can visually represent right away whether I'm inside or outside, for example, my structural checks. So now you can see that the bending moment is above the range that I put there. So this function is really useful to get an interactive way of analyzing your structure, basically. Another function that I find really useful is the unknown load factor. This function basically allows me to solve goal-seek problems using multiple constraints in highly statically indeterminate structures. The concept of the command is similar to what we've just seen with the cable force tuning. So it's again based on the use of load combinations, where I use my permanent loads together with the hanger loads. And the function is again accessed through the result cable control menu. And what this function allows me to do is basically define, as I said, goal-seek analysis. I can use an objective function to find my target, and I can specify the sign of unknowns in terms of positive, both, or negative only. I define constraints through tables. Effectively, the constraints I put here are displacement, maximum of 150 millimeter upward, minimum of 0 millimeter downwards, and constraint in terms of forces in the cables. These are maximum of 900 and minimum of 30, because I don't want cable to go slacking. I select which load cases in the load combinations are unknown. This will be changed in value to meet my constraint. And when I click get unknown load factors, MIDAS has solved the complex problem for me, and it's giving me the factor I need to multiply the load case in the load combination to satisfy the number of constraints that I've given. So we can see the constraint here, and we can see that all of the displacements are between 0.15 and 0, which is what I specified as my target displacement for the tie beam. And if we go to the right, we can see that the hangers are all stressed between 30 and 900 kilonewton, which is what I specified as upper and lower bound for my cable forces. Another part, so when you run this, you can then create a load combination. So you can run multiple scenarios and save the load combinations for each of them and go back to them graphically later in MIDAS. You can also directly create an influence matrix from this function. The influence matrix, what it gives you is basically the factor that impacts each constraint for each different load case in your load combination. An influence matrix can be very, very useful for cable supported bridges, and we will see more about this in a bit. I just want to show you that, as I said, I exported my load combination, and the load combination is accessed in the general panel for load combinations, and the factors there are the factor to multiply that the hangers need to be multiplied by to obtain the results. Okay, As I said, influence matrix are very, very useful in this type of bridges, and this feature was used directly in the River Irwell. What you see here is an extract of the influence matrix for this bridge, where the load combination was made up of the stresses in the hanger, and the response was the stress in all of the other hanger, basically. So if I look at hanger 23 here, for example, and I move along the line, I will find 1. This is the response in hanger 23. What MIDAS is telling me is that if I stress hanger 23 to a certain target force, this will be reflected in hanger 23, which is exactly what we want with the external control force. What is also telling me is that hanger 22 will undergo a reduction of 6.8% in force when a certain force is applied to hanger 23, and 6.2% for hanger 24. Now, if I plot this line, what I get is this plot. This tells me exactly the effect that stressing one hanger, in this case I'm using hanger 23, will have in all the other hangers. And what we can see is that by stressing hanger 23, I have a reduction in stress in hanger 22 and 24, but the biggest reduction is actually in the hanger after the ones next to the hanger I'm stressing, which is 21 and 25 in this case. I can also see how the stressing affects the other hangers and how this reduction and increase ripple through the bridge. And I can see that towards the end of the bridge, as I would expect, I don't get much of an effect by stressing the central hanger. So if I'm trying to lift up the tie beam at this area, it's probably not the best idea to just stress these hangers here and overstress them. Now, what I've shown here is just for hangers, but the influence matrix can be used to determine constraints in displacement, hanger forces, bending moment diagrams, and so on. And I'm leaving you here with a slide of what can be achieved by using influence matrix. This is clearly not the bridge we're discussing, but by using the same concept, you can create an Excel spreadsheet where you export everything of the bridge, in this case, bending moment, deflection, and forces in the stays. And you can control directly the bridge from Excel directly without having to rerun the model every single time. So you can change the imposed tensioning in the wished in place condition, and you will get the final output of the bridge. So as a summary of the functions that I like in this type of bridges, well, first of all, the construction sequencing in MIDAS is easy. It's easy to use because it's made through a graphic interface, or the code is very simple. I also like the fact that I can change the groups as I need. So if the construction staging on site is changing, it's really easy for me to change the groups and rerun the construction analysis. I don't have pre and post subgroups with limitation of elements. The numbering of the elements is not related to the group, and so on. It's really good for complex tapered sections through the use of the taper group function, and this can be used not only for an arch, but for example, if you have a balanced cantilever deck, this is the same function you would use. It's good because it allows me to use fully nonlinear analysis for cable elements when I need it, but it also allows me to use the equivalent secant Ernst modulus for bridges of shorter span, for example. It's possible to do force control directly in the cables rather than having to specify elongation. I like the interactive feature of cable force tuning, and I like the possibility of defining the influence metrics to the unknown load factors. Okay, moving on to the construction sequence for the River Irwell bridge. This is accessed through the load menu, load type construction stage, and then define construction stage. And this is the graphic input that I'm showing here. The whole idea, as I said, is based on the use of element groups, boundary groups, and load groups, which are activated and deactivated as needed, basically. So you need to make sure that in your model you're using the group functions, because otherwise you won't be able to use the construction sequence analysis features. Okay, moving on to the River Irwell bridge. The construction of this bridge starts from the construction of the tie beam at the north side. These are supported on asymmetric towers, as we discussed, and you can see the asymmetric towers here in elevation and in plan. And then it's time to put in temporary props and the first cross girder and the trimmer beam, and then we follow with all of the other cross girders here, and we erect the central tie beam, and then we continue in a very similar manner. So how do I model this directly into MIDAS? So what I want to represent is this first stage 3, and then this at the end of all I did. Please notice that when the central tie beam is erected against the over its temporary supports, there is no connection between the central part and the northern part, and this needs to be reflected in our modeling. Okay, so this is done through the use of groups, as I said. So the first stage will be the activation of the tie beams, the end arch nodes, and the support for the trimmer beam. The second stage is we also at the same stage, sorry, we also activate the boundary groups. And the stage after will be the activation of the new elements. So the first cross girder, the temporary props, and the north trimmer, and we'll also activate the loads inside the temporary props. And then we activate all of the cross beams, as you can see here. As I said, the central part of the tie beam is not connected directly to the north tie beam. This connection will happen later on during the construction stage. So we need to activate the moment release and a shear forces release at this location. And this is easily done in MIDAS by using the beam end release function. So you select in this case, I've selected the J node. You can see it's the end node. The local axis of the beams is going against the global axis, so in this direction as I'm moving my mouse. And effectively what I've released here is the shear forces and all of the moments. So there is no passage of moments and shear forces at these nodes. And please remember to activate the boundary group when you want to use beam end releases, because you want to activate them and deactivate them through the construction stage analysis. Moving on through the construction, it's time then to put up the tie beams at the south end, the props, the cross girders, and repeat pretty much what we saw before. So this is what we will see throughout the construction. And this is again done in the very same way. So we activate the elements and we activate the loads. And if we needed to deactivate any loads, we would have deactivated the loads. So effectively where we got now, the bridge is in this condition, right? So we modeled all of this and it's done through grouping really. Okay, the next stage will be then to prepare the bridge to have a working platform, to prepare the bridge to receive the arch, and then to install all of the hangers. The working platform for this bridge is made of the permanent formwork, and on top of it, runner beams are used to move the MUP. The MUP is basically the cherry picker that will be used to move around and stress the hangers as needed during the construction sequence. Now, these elements are not going to give me, they're not going to work compositely with the structure, so they're not going to give me stiffness. There is no point in modeling them as structural elements because it will only complicate the stiffness metrics of the model and nothing else. So these elements have been input in the model not through structure elements, but actually just through loads, okay? So we activate the loads. It's important that this is done because otherwise the deflected shape on site will be different from what is found in the model. So we need to follow exactly every step of the construction sequence on site as we do it. Okay, it's time now to put up the arch. As I said, I hope the video will work. This video is from Skanska on YouTube. So I just took it from there. I'm just gonna speed it up. Basically, the arch is assembled off-site, as you can see. It's tied together by temporary ties, both transversely and longitudinally. And through the use of two cranes, it's lifted in place. This is a very typical way of building the network arch bridge. This crane in particular on the northern end was the biggest crane in the UK at the time available. And the arch is lowered in. And once the arch is lowered, we will need to then create the final connection, okay? So the next steps will be the activation of the arch with the lifting points from the crane still active. Then we will create a site joint, a temporary connections with bars. And this is what the bridge will look like, right, when we land the arch. As I said, we have the temporary ties and we have the supports here. And this is basically done again by activating the groups for element of the arch, the top bracing and the temporary ties, and by activating the boundary groups as needed to represent the lifting points of the crane, and the loads to replicate, for example, the stiffeners and so on. If we look at the values obtained from MIDAS against the values obtained from the erection manual, we can see that the reactions are very close, and there was an error of about 1% between the fabrication drawing and the model in MIDAS at this stage. So it's pretty good fitting. Okay, it's then time to create the welded joints the south and north end. At this stage, the arch will be fully connected and moment will be passed between the knuckle joints at the two extremes and the arch itself. And so the temporary ties can be released. Now, before doing that, as I said, there is some plates that are being used, bolts, and all of these needs to be modeled inside our MIDAS model to follow the displacement during the construction engineering on site. So this is done by using again the moment and moment beam releases. Sorry, for example, at the north end we have a pin support. At the south end, the design considered a connection that was modeled as a roller support. At the same time, the designer imposed the use of bolts to create the temporary moment connections. And when these bolts are tightened, effectively they induce a rotation into the arch, and this rotation needs to be accounted for through the construction stage as a load. And the importance of this is that this will lock in stresses inside the arch. So we impose this rotation, we create the full connection, so we remove all of the pinned connections and roller support, and we actually create a moment connection between the arch and the knuckle joints. And that load basically will have imposed stresses that are within the structure and need to be taken into account, and will have imposed certain deflections that are different from what we would have obtained if we didn't model all of this. So this part requires a lot of care and modeling in MIDAS, and this can be easily done, as you see, through the use of grouping, really. Moving on in the construction, then it's time to install the hangers. The hangers in this bridge were installed one by one and stressed one by one, while the bridge was supported on the temporary structures. And yes, so what this is going to look like is effectively the activation of one element per side each time. So we're going to have this hanger, then this hanger, and this hanger, and so on, and stressing of it. This is done like all other elements in the construction stage. So what we do is we have a structure group for the elements. Hanger 18 in this case is the 21st, hanger 21 to go in the construction, and we activate the element and we stress it. The MUP here is just the position of the cherry picker along the bridge, and it's important to take it into account because this will change again the deflected shape of the bridge during construction, which is one of the control measurements that you have when you're building a bridge. Okay, it's then time to pour the concrete deck. So far, the formwork was there, but no concrete deck was poured. The pouring sequence was divided in 4 parts: south, north, central, south, central, north. And this is done through the construction stage in the very same way we've just seen. So these are elements that are being activated. It is important to activate, however, the wet concrete before to clearly capture the deformation of the structure again. So the first part will be the activation of the wet concrete as a load in the stage CO1, and then the stage after will be called CO1 composite in this case, and effectively the load is deactivated and the elements are activated. It's important that you assign an age to the activation of this element, and this is due to the fact that, as I said earlier when I introduced the model, the orthotropic plate, the concrete orthotropic plate effectively has time-dependent properties associated to it. So the stiffness is built up in MIDAS directly through the Eurocode graph effectively. And if we give 0 here, the element will basically have 0 stiffness. So we must give a certain age here, okay? The phase after the concreting is the restressing to get the end shape at opening day that we want for the deck. And so the restressing is simply done through the application of loads, like just very much in line with what was done for the first stressing. However, here I just used a slightly different technique. So I've used additional steps, and what I have basically is the first step of the construction stage. I've defined 4 additional steps, and then there is the last step, so I can stress 6 cables in this way in one single construction stage. But the idea is the same as you could split this basically in each construction stage for each cable. Okay, now the bridge is ready to take on the remaining loads, among which the moving load. Now, the moving load in MIDAS is defined through load, moving load. It's based on the use of traffic lane and surfaces and the definition of vehicles. I'm not going to spend much time in the definition itself. You can find a lot of material in the MIDAS help manual and website. The vehicles are based on the code of practice that you're using. In this case, it was Eurocode LM71, and you specify your alpha factor, and pretty much everything is specified for you. Codes are kept up to date very constantly, so you will find most of the codes already available for you when using MIDAS Civil. So what we have defined is the lane. We can see there the curved alignment we discussed. One function that I want to point out, because I've seen that people sometimes miss this function, is the moving tracer. The moving tracer is part of the results in MIDAS, and it allows us to basically interrogate the model for each element and obtain the position of the load that will give us, for example, in this case, I'm looking at the maximum force in a hanger for LM71 load case. And this is what the output will look like. So MIDAS will show us the contour lines as well as the position of the load. Loads can be extracted directly from MIDAS and imported into an MCT file, which can be imported in another model. Or, for example, if you need to create a nonlinear analysis, you can extract it and put it together in a load case created by from a load combination. Okay, I'm going to spend some time now to address something that I've seen has created problems before with colleagues, and it's the fact that when you run a moving load analysis in MIDAS and you're using cable elements, you get a warning message that says that cable tension only truss elements are converted to truss elements for moving load analysis. So what this means is that MIDAS automatically will convert our nonlinear element into the truss element, the linearized element that I introduced earlier, right? This may seem like something wrong. So what I did here is I've extracted with the moving load tracer function all of the positions that will give me the minimum result in the cable along the deck for each cable. And then I created an envelope of it. So what you see here is that most cables are not stressed, right? When I run the analysis using the moving load and the influence lines in MIDAS, for the minimum and the envelope of the minimum of the moving load analysis, I see that all of the trusses are in compression. Now, cables are tension only elements. They don't take compression, they will sag. And effectively, this may seem wrong, but we need to consider that we're looking at just the moving load here. The cable in reality will have a component of permanent load. Therefore, these compressions are to be seen as relieving effect of the permanent tension in the cable, okay? Anyway, if you run this, you have 0. So if we combine these effects with the permanent loads, effectively, we can see that with the cables, we get effects that are higher. We got here for this cable, for example, we get 257.1 kilonewton against only 126.2 for the hanger as a truss, right? The same can be said here. This truss is only carrying 10.6 kilonewton, while when we combine the moving load applied as an envelope of all the extraction from the moving load tracers plus the permanent load, it seems like we're being on the safe side here. Before we go on and compare the maximum result, I want to compare this, so the permanent load plus minimum effect of the envelope of moving load on cable elements, nonlinear, with the permanent effect only, again, in the cable element model. And you can see that the results are the same. It's effectively what I'm doing here is wrong, because what I'm doing is I'm using superimposition in a nonlinear analysis, and this is wrong, but can happen because we're used to using superimposition in our day-to-day work. So you're not gonna, the takeaway from this is that if you use cable elements and you use your moving load tracer and you don't combine this load with the permanent loads, you're not gonna capture the relieving effect that the cable will see. Even worse than that though, if we run the same thing and we use superimposition, which is wrong, with the maximum envelope, what you will see is this. So for these cables, I'm combining the moving load maximum effect for each cable with the permanent load. But you can see that the maximum value that I'm coming up with is 510, while if I use my trusses, which will take relieving effect, I'm getting a much higher result. This is because when I use cables, MIDAS will ignore all of those cables that experience the relieving effect for any given position. So if I put my live load here, for example, where my mouse is, these cables are going to get an increase in load, but it's likely that these cables are going to get a relief, right? And as a consequence, these cables are being eliminated from the solution. The stiffness matrix is recalculated for all of those cables that experience tension, but not the ones that are not experiencing tension. The ones in compression, effectively, being relieved, are taken away from my solution. And so when I combine this through a linear combination, this is wrong. Obviously, you can use cable elements and moving loads, but you need to use load cases created from load combination, because this is a non-linear model. So be careful when you use cables, because you're losing your superimposition effectively. Okay, so moving on to the output effectively. I'm not going to spend a lot of time through the structural checks. These are done to the Eurocodes. Bear in mind that when you deal with cable supported structures and slender structures, you end up having for steel sections where local buckling becomes important. So you're likely going to end up using Eurocode 3.18 for the plated structures. Okay. In terms of global stability, this is a very important check for slender structures, again, and particularly for network arches. And the global stability was checked through nonlinear buckling analysis carried out directly in MIDAS Civil by considering the buckling shape from the linear analysis and introducing the imperfections as specified in the Eurocodes, and basically running a nonlinear analysis in material, for finding the load factor associated to failure of a specific element based on the deformed shape from the buckling analysis. Another important case and very demanding case for this structure was the cable out load case. In this case, the structure needed to be safe for any 4 consecutive hangers being accidentally broken. So this was done through the use of a static analysis where the elements were removed and an amplified force was applied statically, and the bridge was checked under these conditions. Okay, moving on to the results obtained from this Cat3 MIDAS model, Cat3 check MIDAS model against the hydraulic jack readings on site. This is the hydraulic jack readings on the temporary towers. You can see that the model predicted pretty well the behavior of the unloading behavior, of the temporary towers. And we can see that for the northeast and the southwest, we're basically spot on completely. There was something not quite being captured correctly here. You can see that we predicted from the red line is the MIDAS model, the black line is the jack on site. What the model predicted was slightly higher forces in this temporary tower to start with, but you can see that even if that was not achieved, the gradient of the curves is fairly similar here, and the stages at which the unloading happened for the southeast was still very well captured by the model. And this can be done to the way the operation happened on site, or temperature on site, for example. Another control that we had during construction was the geometrical survey of the tie beams and the arches. What I'm showing here is the displacement of the arches. So the team on site would get the geometrical reading. These are the points, the green dots, on the graph you can see here. Ignore the lines. This is just used in Excel, used line interpolation between the points, but the points that were received from site team were just this here. And the blue line is the displacements obtained from the MIDAS model throughout the construction stage. This in particular is the first phase of stressing and the installation of the first 10 hangers, really. So the displacement is really well captured by the model, as you can see, and all of the points that were read on site basically lie on the curve of the displaced curve obtained from MIDAS. And we can also see the MIDAS really well captured the point of counterflexure where the deformed shape would change. And this was a very encouraging result. Obviously, when you're building a bridge like this, you want to have control and you want to make sure that your analyses are matching reality. And the same is done here for the tie beams at the same stage. And you can see that MIDAS has captured very well the deformed shapes throughout. In particular, you can see here that we have one red dot, that's the top flange of the tie beam, and one green dot that are very far apart. This is not a good reading from site, and it would basically mean that the tie beam is stretching along its steps or something like that. So it doesn't make sense. It's wrong reading from site. But overall, the shapes from MIDAS model really follow well what happened on site. And the same happened throughout the construction sequence. Obviously, this was done almost daily during construction, and models were corrected to match the right basically stressing level read on the hangers. And as a consequence of all of this control, a new stressing sequence was issued, produced by the designer, checked by us, the cut-through checker, and was issued to the site construction team. And this is the same at the end of phase 1 stressing. Okay, we're good on time. Last slide. I'm just going to show here how the MIDAS model predicted the behavior of the cables on site, and how by using a detailed analysis during construction, matching the displacement of the red on site, we managed to get even better fitting. So these graphs show in the red curve the PIN structural monitoring system reading. This is an ultrasound based structural health monitoring system. The yellow line is showing the strain gauge system used on site. The purple line is showing what is called the back analysis. So this was the analysis that was ran in parallel with the construction sequence, following exactly the step happening on site and matching the displacement. And the for construction is basically the original analysis that AECOM carried out on the cut-through check of this structure. Okay, so you can see that MIDAS well interpreted the behavior of the hangars when you compare it to the structural health monitoring system on site, and this can be said for the hangars throughout the construction. You can see here various graphs. What I want to point out is that by going into the details of the construction stage analysis and all of the nodal connectivity and so on when the arch went on, we can see that the back analysis shows this behavior. It's basically like a sawtooth behavior that we saw from the structural health monitoring, which was not predicted in the original models. But you can see that by modifying and replicating everything, the MIDAS model has given very good accuracy. And even when the structural health monitoring on site, you can see here the yellow and the red line, did not quite match, the MIDAS model actually happened to be right in between, basically. So this was of great comfort for us as checker. The designer was getting similar results. These were being communicated between us, and we were comparing results constantly, almost on the daily, during the erection of the arch and the stressing sequence. And obviously also the construction team on site. So having a finite element model that gives you exactly the displacement, exactly the forces that you're reading on site is a good comfort, and it's the only construction control that we have when we're building long span bridges on site, really. So MIDAS was really useful for this project, and it was really a good software, and I highly recommend using it for your project when you're dealing with cable supported structures. This is it from me. I'm gonna try to take some questions now. There's not a lot of time left, but maybe we can answer some live. If I don't manage to answer your questions, I will do my best to get within reasonable time back to you, and the responses will obviously be distributed to everyone on the call. If there is anything that comes to your mind later on, please feel free to contact me. Those are my personal contact, work email, and LinkedIn. And in case you didn't know, we now have a new official blog that MIDAS has made available for all of us, and it's full of know-how shared directly by us engineers doing the work with MIDAS. So I highly recommend you go check out this blog, because you can find a lot of interesting articles and know-how, and find out how to do things that you may need to do.